Hello, and welcome to Dr. Cossey's discussion on elimination reactions. Today we're going to talk a little bit about E2 and E1 reactions, basically an introduction. So since we've been talking about substitution reactions, I thought it would make sense to compare elimination reactions to substitution reactions first, just so we can put everything in context. Elimination and substitution reactions have some things in common. One thing they have in common is the substrate. So they should both have an R with a leaving group, and that's going to be common for both of them. And they're both also going to have a nucleophile of some sort. They, of course, have some things different as well. The most obvious thing that's different is the product. The product will be an alkene for an elimination reaction instead of a substitution where it's got some new functional group on it. The other thing that is different is you'll use heat for elimination reactions, and that's because heat will favor elimination over substitution. All right, so now let's look at an example of an elimination reaction. So if you look at the reaction shown at the top, basically you have a substrate, right? You have carbons with leaving group, then you have a strong nucleophile, and then that thing underneath is just a solvent, that's ethanol. So that's basically just like the nucleophile, but with a hydrogen instead of a sodium. So basically, those are the reagents. Now, what you would normally think is if you have a tertiary, that you would have an SN1, right? So that's actually one of the byproducts over here that you could have. But actually, that's a minor product. Instead, because you have a strong base instead of a weak nucleophile, like we prefer for SN1, instead you get this elimination reaction. So that's going to be the major product. Now, what's the mechanism of this? So basically what you're going to have is you're removing some stuff. So if you look at the product, what's missing from the product that's shown in the starting material? Right? Obviously the Br, right? But what else is missing on the other carbon? Right? We're missing a hydrogen. So if you look over here, we've got 2 hydrogens. And if you look on the left, we've got 3 hydrogens. So that's what the elimination is. You're losing things, not gaining anything. So we're losing an H and a Br. So what's going to happen is an acid-base reaction. So we're going to have this strong nucleophile. We're going to redraw it with a minus charge. And that's what's going to come and remove the hydrogen. And this happens all in one step. So we're going to take this hydrogen here and attack that. And then the electrons from that hydrogen, instead of just going to make a C minus, they actually go to make that double bond. So they go in the middle. And then because they're going there, that causes the Br to come off. So that happens all in one step. You've got 3 arrows. Okay? Now, we know that this can happen, this is the major product, but we can make it even better by adding heat. So the way that organic chemists write heat is this triangle here. So that means heat. A few other things about this reaction before we move on, some details. So basically it's E2, so we know that means, so far it's elimination, right? That's the E, but also the 2 means bimolecular, just like SN2. So whenever we have something that's bimolecular, that means that the key step in the kinetics, like the slow step, is going to involve 2 things. So in this case, it involves one thing, which is the substrate, and the second thing is the base. So those are going to be the 2 molecules that you see in the key step. And this only has 1 step, so that makes sense. Okay? The next thing is it does require a strong base. So you have to have something with a pKa of at least 15. We're generally going to use some sort of alkyl, alkoxide is what they're called, an alkyl group with an O- on it. Okay? And the other thing is you want to make sure you put that heat on if that's the product you want, which obviously in this case it is. Okay? All right, so let's talk a little bit more about this reaction in detail. If we look up here, we notice that we took the hydrogen on the right side. But for this product, would it matter which hydrogen we took? No, right? Because no matter which hydrogen we take, if we take it off this carbon on the left, we'd still get a major product that looks like this, but that's the same molecule, right? If we were to name that, that's an identical product. So the question is, what happens if it's not identical all the way around? This is very symmetrical. So let's look at another example. All right, so looking at this reaction at the top, you notice we still have a Br, right? And now there's a couple of different double bonds that we can make. So if you look, I've drawn 2 possible products on the right. So the first one comes from taking off the hydrogen on carbon 2, right? So this carbon right here. And then if I take that one, I get this double bond. And then the other option is taking the hydrogen off carbon 4, right? I could also take the hydrogen off the carbon on the bottom here, but then that's going to make this product. And if you look, that one's identical to a different product. Which one is it the same as? Right? It's the same as the one on the right. So I don't need to draw that because it's identical. Okay? So the question is, are we going to get both products or is one of these going to be favored? So we know that eliminations are regiospecific. So regiospecific means that one isomer is preferred over another. So that means we're going to have a major product. So in this case, when there's a choice, elimination reactions usually favor the most stable alkene. So the major product would be the one on the left and not the one on the right. That would be minor product. Now, it does depend on the base. There is a way to get the other option if you want to, but right now we're just going to focus on the major, more stable product. Okay? So the next thing we need to know about is this thing called Zaitsev's product. That's just the product of a normal elimination with this kind of base. So basically that just means the more stable alkene. So Zaitsev product equals the most stable alkene. This is the product that you get whenever you use sodium ethoxide. That's the base we have here, or any sort of small skinny base. All right? Now, just to make sure we're clear, we'll talk about alkane stability. So when you have alkane stability, generally you want things that are more substituted, meaning they have more carbons attached to the double bond. So if you look at this one has 4 carbons attached to the carbons with the double bond, right? So if this is the double bond, 1, 2, 3, 4. Okay? So then if I have 3, that would obviously be not as good, but slightly worse. And then if I have 2, there's actually 2 choices. So I have cis or trans. Trans is actually more stable because of sterics, and then cis. And then the last one we'd have would be one thing on the double bond, right? So then stability, this is the most stable because it has the most carbons attached to the carbon double bond. And this one has the least, so it would be the least stable. So if that doesn't make sense, just let me know. Sometimes people get confused about the more substituted part about this, but if you're confused, just let me know. So knowing that, the take-home message is if you use sodium ethoxide, which is the most commonly used base, you're going to get the major product, which is going to be the more substituted or more stable double bond that we see at the top. Okay? Okay. All right, so as we said, the previous reaction that we saw was an E2 reaction. So before you move on, let's talk about how an E2 would be different from an E1, okay? So as we said, an E2 is what's shown on the left. We've got our normal sodium ethoxide, ethanol as the solvent, and heat. Our major product's going to be the more substituted double bond. So what's that going to look like? Would it be to the left, to the bottom, or to the right, the double bond? Right, it's going to be, you could say either to the left or to the bottom. They're actually symmetrical, so either one's fine. So I'm going to draw it this way, and that's going to be my major product, right? So E2 is going to give me the most stable double bond, the Zaitsev product, and the mechanism would look like this, right? If this is my double bond, I need to take off the hydrogen that's going to make that double bond. So I'll redraw my base with a negative charge, get the hydrogen, bond breaks to make a double bond, and then the bond of the Br breaks. All right? So that's the mechanism. All one step. We should have 3 arrows, and then it has 2 different molecules that are coming together in the key step. That's what makes it bimolecular. The other thing we want to remember is that E2s come from a strong base. So you see our strong base here is this O- here. E1s are going to be a little bit different. So one way that we can get an E1 reaction is to use a weak base instead of a strong base. So we're using a nucleophile that's a weak base. So that would be this one here. It's still going to form the most stable double bond, so this product. And so what do we think is going to be different about an E1 versus an E2 mechanism-wise? It has something in common with SN1. So what was special about an SN1 versus an SN2? Right, it had a carbocation. So an E1 is also going to have a carbocation. So basically that's going to be the main difference is the mechanism. So the first step of the mechanism for an E1 is the leaving group leaves, just like SN1, right? So you draw your carbocation, that's going to be tertiary, right? And then the next thing that's going to happen to get to the product is we have to remove the hydrogen. So what can come and remove that hydrogen? Right, we probably want to use the nucleophile. That's still a better base than Br minus, so we're going to use the nucleophile that we have, and then that's going to take the hydrogen away and give us still the most stable double bond. Now, the other thing that's different about this is even if we heat it, this is not going to be the major product. So if you use a weak base, it's really hard to get elimination. So your major product is going to be the SN1 reaction. So that'd be this reaction shown here. So generally, if I ask you to show the mechanism, I'll just draw the double bond product and I'll say minor product. So it'll be clear that's what you're supposed to draw it for. But just know, like if I was doing a box question, that would not go in the box. The thing that would go in the box would be the SN1 because that's the most common. For the reaction on the left, this is the major product, so that would be what goes in the box for that one. But just you only want to put the major product for whatever it is. We'll talk more about how to make a decision between an SN1 and an E1 later, okay? Okay, so hopefully that makes sense. Let me know if you have any questions, and we can talk more about it in class. All right, so hopefully that all makes sense so far. There's one more thing I want to talk about, but I don't want this video to go too long, so I'm going to make it in the next video. All right, so I hope to see you in the next video. Thanks, bye.